Good evening. Joanna, if we could get you to take your seat. And if the rest of you could please check that your phones are on silent, we'll begin. My name is Dawn McMaster. On behalf of the directors of the NLC, as well as the program committee that brings you this space series, I welcome you to an evening of learning and connecting. We begin with a land acknowledgement. This place where we gather is in the traditional and treaty territory of the Mississauga and Chippewa nations. We offer our gratitude to the First Peoples for their care and teachings about our earth and relations. May we honor those teachings. I'd also like to thank Ed and Sylvia Van Haverbeek, who through their family foundation have sponsored this space series. And we offer our gratitude to Corey Simpson, our first ever educational sponsor, who is providing tickets to students to attend our event. And we especially welcome our students this evening. Tonight's presentation by Dr. Cassandra Marion is titled Lunar Exploration and the Path to Mars. Cassandra, who likes to be called Cass, holds a PhD in Geology and Planetary Science and Exploration from the Institute for Earth and Space Exploration at Western University. She is a science advisor for the Canada Aviation and Space Museum and is a passionate science educator who works hard to improve science literacy across Canada. Cass's research expertise is in meteorite impact craters in Canada's north, which work well as proxies for these features on the lunar and Martian landscape. As a result, she helps train and prepare for real missions to the moon and Mars. To quote the Canadian Space Agency, she is an expert in all things analog missions. That is, simulated space exploration missions designed to train, test, and learn in preparation for real robotic and human space exploration. Most recently, Cass trained 2 Canadian astronauts in field geology in preparation for their upcoming missions to the moon. Let's give us a warm welcome to Dr. Cassandra Marion.
Thank you. Always. Hello, everyone. All right, mic test, check. Thank you, sir. How are we doing? Ready to hear about the moon and Mars? All right. So thank you for that wonderful intro. It's wonderful to be invited to this very special space series. I was excited to hear about your space-themed thing, and all of the speakers for this series are amazing. So I'm honored to be amongst them. So I have, as she mentioned, basically the wonderful job at the museum of basically sharing the cool, awesome things going on in space exploration. And tonight it's all going to be about lunar exploration and the path to Mars. So you may or may not know that the international space community has basically decided to go back to the moon. We are putting boots on the ground once again, but we're going to do it in a sustainable way. We're going to do it in a collaborative way. So internationally, we're going to work together to get there. And when I say work together, actually work together, which is very different. And, you might pose a couple of questions right off the bat. Why? Why now, after 50-some years, are we going back to the moon? What's so special about the moon? Do we still have stuff to learn? I thought we already went to the moon, right? I get these questions quite often. And then, what role is Canada playing? And so the quick answers are the moon is a time capsule that preserves the evolution and the history of not only the formation of the moon, but also the formation of Earth and our solar system as a whole, because the surface is really very unaltered compared to Earth, which is very geologically active. We've got plate tectonics, we were covered in oceans, and so our early history is not preserved in our rocks like it is on the moon. And so the more we understand about the moon, the more we understand about the Earth. The other thing, the answer to the why we're going back now, is we've identified some resources that we can use in place on the moon, and the main one is water ice, to make working there and living there feasible, practical, and economical. All right, and then I'll get into what Canada's role is too. All right. So we're going to start by approach to exploration. Generally speaking, we don't operate on the boldly go of Star Trek. We don't just go and explore and wing it, right? Although that would come up with some really fun stories. Generally speaking, we take stepwise approach. It's an incremental learning, testing, experimenting, developing the technology to get there, and then we take the next step when we're ready and when it's safe. It's always risk mitigation. It's always planning. Now, and from lessons learned from Apollo, everything is before we even send any mission, it's people sitting around a room coming up with the long list of what could potentially go wrong. We find answers to address those what's going to go wrong before we ever launch something, right? To avoid situations like Apollo 13, where you have to figure out solutions on the, with lives at risk. So that's what we do. The first thing, you want to go to the moon, we have to really understand the lunar environment first. What is it like on the moon? Maybe John mentioned the moon. I think he did Mars last week. But what is the environment like? It's an airless body. It's really cold. And then we have to practice getting there first. Orbital dynamics, basically getting spacecraft to the moon, to orbit where we want them, to land where we want them. That takes time and that takes practice. So the first thing we do is we send orbiters. Once the orbiters are checked off the list and they've collected a lot of data, then we send landers, then we send rovers. Then, once we've got all that down, then we consider creating a human-rated spacecraft like the Orion spacecraft here, a landing system that can get boots on the ground. Then you've got to develop new spacesuits, which they just announced, the new ones that are going to be walking on the moon. From Axiom Space. And once that's all established, then you can think about actually living on the moon, working on the moon in any sustainable long-term way. And that's basically what we've done in the past too. So if you look at this lunar timeline, this is from the Lunar and Planetary Institute. I know it's really tiny, but all you need to do is recognize how many dots are on there. All right, so let's see if I can point this out. So we're starting in 1959. This goes to 1998, 2003, and then till about now. But if you look, we started sending spacecraft to the moon in 1959. And when I say we, I'm going to say we a lot. I don't mean me. I mean the people of Earth. So internationally, so this diagram includes, China's, the Soviet Union's spacecraft, etc. These are all things. So we, as a people, started sending spacecraft a long time ago. And oops, I skipped that one. I wanted my laser pointer. This is sort of the Apollo era here, okay? But before Apollo 11, the first boots on the ground, there were more than 20 precursor spacecraft missions sent to the moon. That's something that's probably coming as a surprise for you, right? There were many an orbiter by multiple nations. There were many a lander. There were even rovers by the Soviets, called lunokhodies. And all of that in place, and even the Apollo program, we sent Apollo 8. That was just the capsule, astronauts in it. They went around the moon and they came back, but they didn't land, and that was on purpose. Everything was stepwise. We learned to get around the moon. We learned to do, rendezvous and docking in orbit before we ever attempted to send a lander down and come back up and dock. We made sure we know how to do that first. So everything is stepwise. Make sure you know how to do it before you put your very precious astronauts' lives at risk, and expensive spacecraft as well. So we've got through the early 69 to 72. That's the Apollo area. Then we had political and financial support went downhill quick, and Apollo got canceled. And then there's a little bit of a lull here through the 80s. The Soviets still sent landers. They actually last sampled the moon in 1976. That's the Luna 24 mission. And then after that, it's not that we lost interest in the moon. So this is the thing that you have to also understand is us scientists, we still think the moon is awesome and there's tons to learn, and we're still today looking at Apollo samples. Some 60% of Apollo samples are still archived. We've never taken them out of the box. Okay? There's still tons to learn. And even the data from pretty much any of these spacecraft that were collecting scientific information is still usable, and we can re-look at it now with new eyes, with the new knowledge that we have, right? So nothing is lost, even though some of this is old, it's actually still very useful. Then, early 90s, we started sending spacecraft back. We got some funding. The scientists were really happy. They finally got some support. Started spending some new orbiters around the 90s and then into the early 2000s. And you'll see, boom, there's a huge boom here in the early 2000s. And that's because the Lunar Prospector, one of these guys over here, it identified the potential for water ice found on the moon. We thought for a long time that the moon was very dry. And in general, it is. The rocks are they're really dry rocks. There's no water ice, in the mid-latitudes to equatorial region, okay, around the moon. But what they did find is evidence for water ice near the lunar poles. And then they wanted to make sure that it was actually water ice. This was suggested a long time ago, but they didn't really have the evidence to back it. And so a series of these orbiters, not all of them, they had a variety of objectives, went to confirm that. And so one after the other, is actually now 6 spacecraft that have measured either hydrogen, water ice, or hydroxyl, which is just an oxygen and hydrogen atom or a molecule found there. So that was some of that thing. We'll talk about some of the data that comes from this. And then you'll see a lull. This is the Lunar Reconnaissance Orbiter. It's still in operation. It was launched in 2009, and it's still sending us amazing data. So you're going to see a lot of that today. And then now we have the new phase, the Artemis program, and the return to the moon is happening now. This is the line marking today. What is not captured is what will be here in the next decade. This is going to be there'll be a lot of dots on this graph. Right now, this year alone, there's 3 other missions heading to the moon before the end of the year. Okay? And there were about 10 between now and last time this year. Okay? Not all of them were successful. And that's pretty common. Like I said, we're learning as we go. And some of the examples, you might think, oh yeah, NASA knows how to get there, but the folks that got us there in the Apollo days, they're all retired. Okay? And also we have new nations putting things on the moon. And so India just landed on the south pole of the moon. China has a rover roving on the far side of the moon right now. Okay? So it's not just one nation. Now, going back in time, we'll talk about Apollo a little bit and where Canada fits in that picture. I don't know if you know, but Canada did actually play a series of roles in getting people to the moon. Does anyone know about the Avro Arrow? This crowd probably does. Okay, yes. So during the Avro Arrow days, 1959, we were making a supersonic aircraft. It was supposed to be an anti-missile aircraft. And that program started, was going awesome. We had these, the best and brightest engineers working on it. And then the program up and got canceled. And now, a lot of engineers are out of the job. And within 4 months' time, NASA interviewed and hired 32 of those engineers, 12 of which were native Canadians. Some of them were immigrants from England and so on. But for the most part, there was about a dozen Canadians that went to join the Space Task Force to get humans to the moon. A lot of famous ones. Owen Maynard, for one example, he became chief of the LEM. This is the Lunar Landing Module. He was the chief engineer for that, helped design it, and he was in mission control that whole time. Also, Canadian technology is on that lander. Our STEM antennas, these tubular antennas, like a metal fruit roll-up, it unfurls, and as it unfurls, it makes a tubular metal, basically a long metal tube. You can make an antenna, if you're gonna launch something on top of the rocket, you kind of wanna tightly pack it before it gets into space. And then once it gets into space, you can extend an antenna tens of meters long. Okay, so that's significantly increasing. Either you can use it for actual data, so let's say HF radio, giving you a much stronger signal, or easier communication back to Earth, and so on. So there are STEM antennas. That is a technology that was on Canada's very first satellite, the Alouette. And from that day forward, that really is that antenna started Canada's role in space. Also, the lunar landing gear. 9 out of 10 parts of that landing gear Canadian made by a company called Héroux in Longueuil, Quebec. And so you can say now that there are actually 24 Canadian legs on the surface of the moon. Huh? Tell your neighbors. Okay. We didn't make the foot pad, so you can't say we're like standing on the moon. It's just the leg. But the reason when they got chosen is because they basically made this telescopic leg. So technology on the moon, because you're in vacuum and it's extremely cold or extremely hot, you couldn't work with all the typical landing technologies. And so what they were really good at was working with aluminum. So they made this telescopic leg, so like two tubes, one fitting into the other. And they made the honeycomb of aluminum inside the top of that leg, and that's what absorbed the shock. So as it lands, the smaller leg drives up into that honeycomb, the honeycomb gets crushed, and it's the aluminum that is absorbing the shock. Turns out they weren't sure, especially for Apollo 11, how soft the regolith, how soft the lunar soil was going to be when they landed. And it turned out the first landing it didn't actually need to crush very much of that aluminum. It was like a really smooth landing, even though they were almost out of fuel. That's another story. But yeah, so, and then that's not all. We also trained some of those Apollo astronauts in Sudbury, Ontario, in the second largest impact crater on the planet. This is Charlie Duke and John Young. They're training for Apollo 16, and that's a picture of them in Ontario, Canada, before they took off. All right. So still looking at Apollo and keeping this incremental learning approach in mind, okay? If you look at where we landed, I'll start with this. You'll see that most of the landing sites are in sort of on the near side of the moon, and they're in the mid-latitudes to middle region of the near side of the moon. There are many other landings, so there's a lot of robotics that landed on the moon, but they're all almost always sort of in this region. Only in the last couple of years have we had things land on the far side and near the South Pole, okay? Only in the last 5 years. But at this time, all we explored was this part of the moon, which is a very narrow window. If you tried to land only 6 places, even if you took a vacation in only 6 places on the Earth, do you think you have a really good idea of what all of Earth is like? No, there's so much of the moon that we have not explored and that we don't know very much about, with the exception of sort of an orbiter's view, okay? But you'll see, okay, we got Apollo 11 up here. We've got LM 21 hours. That's how long the lander was on the surface. And if you look at EVA hours, that's how long. EVA is extravehicular activity. That means when they stepped outside of the lunar module and their spacesuits and they were walking on the surface, okay? So if you look, only 21 hours, Apollo 11 was actually on the surface. Half of that time they were sleeping, okay? And only 2.5 hours were they actually, one small step for man, one large step for humanity. I can't do the accent. But you'll see that as time goes on, both of those times increase. They got more confident and they extended the mission. So 2.5 hours to 22 hours on the surface for Apollo 17. Okay? Stepwise. Now, the Lunar Reconnaissance Orbiter. This is the orbiter that's been in orbit since 2009. It has these amazing high-resolution cameras that it orbited just 22 kilometers above the surface and took close-up images of every single Apollo landed site. So you can see where the lunar landing modules are. You can actually see footstep tracks. You can see some of the instrumentation they put out. There were basically an instrument package for each of these missions that they set out. In these 3 missions, 15, 16, 17, they had a lunar roving vehicle, basically like a dune buggy that they got on in their spacesuits so that they could go farther, because actually moving in the spacesuit, or it's like a bunny hop thing, is a bit of a challenge. And they're mostly flyboys at the time, so they gunned it a little bit more than they should have. But I think the max speed was only about 12 kilometers an hour, but that in lunar gravity, and then it's like kind of getting some airtime, if you can imagine. And then the regolith is really, really squishy. So that's fun. But now it looks like someone's been ATVing around the moon, right? Okay. A couple of things I'll point out too. You can see that there's lots of small craters. Apollo 11, one of the reasons they almost ran out of fuel is because their desired landing site, when they got there, it was full of boulders. And then, so the pilot at the time was like, I don't think I'm going to land here. This is not a good news. So he basically overshot the landing on purpose just until they were like driving on fumes and then put it down. So that he was landed somewhere where there wasn't a boulder field. Okay. The other thing, so some of the instruments that they put out, usually they're geophysical instruments. So seismometers. Yes, the moon has earthquakes, but they're like mini quakes, and they do really weird things. And they last, an earthquake on the moon actually lasts something like 10 minutes long instead of a couple of minutes. On Earth, we have oceans that like muffle our signal and other things going on. But on the moon, earthquakes are weird. Can't tell you too much more. I'm not a geophysicist, but we do have one in the room. So maybe I'll ask that question later. But the magnetic field, there are magnetometer they put out. The moon no longer has a magnetic field. It once probably did, though. And you'll also see in the instrument package this little bright dot here, that white dot. That is actually a reflector, giant panel of mirrors. And Apollo 11, 14, and 15, they put out these retro reflectors. And what we do is we take a laser from Earth, we point it at the reflector, we send that, basically a beam of light to it, and then it bounces back and comes back to us. We know the speed of light and the time it takes for us to get that signal back, and with that we can calculate the precise distance between the Earth and the moon. And we have been doing this for 50 years. And so we now know that the moon is moving away from us at 4 centimeters a year. So now think of, at some point, the moon was a whole lot closer and a whole lot bigger in the sky. Right? I'll tell you just how much in a minute. This is an image from Apollo 17. This is Harrison Schmitt, the only geologist, so of course he's my favorite Apollo astronaut, the only actual geologist to ever set foot on the moon. And because they had a geologist astronaut at that time, it is the most scientific return mission that they had. Also because it was the longest and the last. But when you actually have a geologist on the ground, it does make a big difference. So we brought back 842 pounds or 382 kilograms of moon rocks. The Soviets also brought some back. And so did China most recently, but very small amounts, in 2 sort of touching grab-and-go missions very recently. But of those rocks, and from these missions, and including the orbital missions at that time, we've learned a bunch of stuff about the moon. We know we've used radiometric dating to determine the age of some of these rocks. You can't always just take a rock and give it an age. You need context. You need to be able to explain where that rock came from to understand what that age means. So it may not be the age of a rock, it might be the event that it underwent most recently. Because when you heat a rock, you actually reset its age. Won't get too far down that rabbit hole. We can hit it in Q&A if you want. We understand that the chemical compositions of the moon are very similar to the Earth. So we actually look at oxygen isotopic values. And that's just one chemical way that we can link that the rocks are from the same source. Okay. We also know, based on the actual mineralogy, the geology of the different parts of the moon, that the moon once was entirely molten. We call that the lunar magma ocean. So was Earth at one time. And as that magma ocean cooled, that's how we have the division of core, mantle, and crust. Okay, so all of the heavy elements and minerals, they sink down to the center, the moderate ones in the middle and the mantle, and then the lighter minerals, such as what you're seeing in that image right now, they float up at the top as it's cooling over time. That's what we call a differentiated body, and it's because it was fully melted. So with that knowledge, we also know that the lunar surface is heavily bombarded. So it's jam-packed with craters, which is, my favorite thing. But because that, all of the regolith is just mashed up rock. We call it's just full of breccias. It's also full of tiny little glass shards, which the smaller particles of those are what we call lunar dust. Lunar dust is very statically charged. It sticks to spacesuits. It gets in everything, and it's very, very sharp. So it's always something to consider too. Some of their instrumentation, or actually they're also measuring solar wind, so solar radiation, and trying to evaluate the dust later years. When they had no way of predicting the dust problem the first time they landed. And then when those suits came back, they were dirty. Okay, so with all the information, this was not a new proposal at the time, but with that information, the hypothesis on how the moon formed, this is the hypothesis that fits the best, and it's called the giant impact hypothesis. I will tell you now, though, a lot of things that happen in space, when we can't explain them, we're like, something hit it. It's pretty much the go-to. Uranus is tilted on its side, something hit it. Okay, but actually makes sense when you do the modeling, okay? So the idea is baby Earth, or proto-Earth, okay, early Earth, at some point, 4.5 billion years ago, because we now have actual dated rocks, was impacted by a Mars-sized object, which they've dubbed Theia. Now, Theia, it wasn't a dead-on collision, it was like a passing graze, okay? And what happened was all that material after the impact, both of them become magma oceans. Earth becomes a magma ocean, and then all of that debris from the impact becomes in orbit around the moon, around the Earth, and it coalesced, if you will, or accreted, which is usually we call, that's the typical term when we're talking planet or moon formation. All of the bits stuck together to form a body. And that's what formed the moon. We believe there was actually a second smaller body that impacted the moon soon after. Now there's something called the Roche limit, and that is a space around the moon, or around the Earth, or any planetary object, in which material will accrete, will stick together and form something. And within that, if you're too close to the Earth, you can actually have something come together. So think about Saturn's rings that are full of dust particles, right, and ice. Those are within the Roche limit. Those dust particles, they will never form a little moon to go around Saturn because they can't, okay, because of the pull of Saturn's gravity. But beyond the Roche limit, which is different for every mass, you can. And so we know that the moon had to form outside of that, okay? Now, I told you that we measured the moon moving 4 centimeters a year. So if you reverse calculate that, and you keep the Roche limit in mind, which is about only 2 Earth diameters, that's about, in this version of the moon, where it formed 4.5 billion years ago. And over time, has moved away. Now, really cool is the moon being around the Earth, it stabilized our orbit. Okay, and it also changes the length of our day. Think about the tides, okay? Now there's solid tides. So the moon's early formation, our day was about 5 hours. And the moon would have been 16 times the size in the sky. Okay, and it would have like, looking it up, it would have overtaken the sky. It would have been quite the sight to see. I hope they do like another Star Wars where that's something the case is really nice. All those visual effects. But now today, it has moved so much, it's about 384,000 kilometers away on average, because it's not a perfectly circular orbit. All right, it's also tidally locked, so we always see the same side of the moon, our near side. Now, let's look. This is the near side, and of course, until we had spacecraft, we never knew what the far side looked like, and so we didn't know that they were really different. All right? So on the near side, and the far side, and the moon as a whole, I'm sorry if I'm blocking anyone, they're very different, but there are 2 main terrains on the moon, okay? We know that we have what's called the lunar highlands, which is most of the far side, and then we have what's called the lunar mare. The highlands represent that light floated, the minerals that were really light, that floated to the top of that magma ocean, and that formed the moon's crust. The lunar mare means seas. these are actually volcanic lava flows that filled in ancient giant craters, okay, basins. So yes, there were volcanoes on the moon. They're no longer active, but they're basically basaltic in composition, although they're not all exactly the same composition. But you can think the composition of sort of lava from volcanoes in Hawaii, if you will, okay? So they're lunar basalts, and that's why they're smooth plains, is because it was molten and it was liquid, and as it expanded and cooled, it was pretty smooth. You'll also notice that there's not as many craters on top of them. Okay. Other things about this one, I'll come back to it. Let's do another view. These colors represent topography. Oh, and I'm going to walk in front of a selfie thing here. So if you're looking at the colors, you've got higher topography is red and white in here, and the lowest is down here in the sort of South Pole region of the far side. Near side, pretty boring. Of course, the thing that we see all the time is kind of boring. But if you take the highest part on the moon and then compare it to the lowest part of the moon, there's 14 kilometers difference. But if I do the same thing from Earth, so the top of Everest to the bottom of the Marianas Trench, it's only 11 kilometers. There is a much bigger topographic difference on the moon, but only on the far side. If you're wondering what this giant low point is this is a huge impact crater, the largest on the moon. It's 25 kilometers in diameter, called the South Pole Aitken Basin. And that's one of the places we want to go check out, because it's the only place on the moon where it's possible that it excavated down to the mantle. So through the moon's crust, we have a really hard time looking at the mantle of the Earth. We don't understand, we have very few places on Earth where you're actually exposing. We have exposures of the lower crust, but we don't have exposures of the mantle. So if we could find that out on the moon, that would be pretty epic for geologists. All right, other types of data. These are all false colors. This is the Galileo spacecraft. I think it was launched in '96. And it's taking, these are information on spectroscopy. So we're basically using a variety of different instruments that detect light. And we're looking at different wavelengths, and information from those wavelengths tell us what minerals are there, okay? What elements, what is it made out of? So every different color is a different composition in both of these situations. They're just looking at different wavelengths, and so they're both really weird comparing. And so even from the 90s, we knew that the moon's geology was variable, okay? Outside of the large terrains. And then if you look at, this is actually an Indian orbiter called the Chandrayaan-1, and it had an American instrument on board called M-Cube, the Moon Mineralogy Mapper, and it mapped almost all of the moon for mineralogy. And the bright greens and blues, those represent mostly iron compositions. And this is the near side. This is looking at the side of the moon. This is actually the mare over here. And so you can see there's a huge difference in composition between the highlands and those mare. With that information, we also made geologic maps. So this is someone that went in and mapped, based on that spectroscopy, all those different colors information, and made a map. Some folks do their entire master's or PhD thesis just taking one tiny little crater around the moon and mapping it, and they take 3 years to do that. Okay? So there are some parts of the moon we know a lot more than others. Sometimes it's about time spent, and sometimes we just don't have the data. But in a general way, in an orbital view, we know a lot about the moon. But once you're on site, once you have boots on the ground, then you're correcting all of your interpretations from orbit, right? They're not always right. And you won't know until you get there. And that's actually some of the work that I've been doing most recently, is comparing spectroscopy from orbit to spectroscopy in a handheld instrument on the ground, and then you take that same rock, you bring it into a laboratory, and you zap it again with the same instrument but different scales. Are they the same? Do you come up with the same interpretations? Sometimes yes, sometimes no. All right, another form of information we get, this is the GRAIL mission, Gravity Recovery and Interior Laboratory, short for. And it was 2 twin orbiters called Ebb and Flow, which they were dubbed later. But it's clever naming, right? And basically they would orbit around the moon at opposite sides, and they would be detecting basically the changes in mass and density using gravimeters and other tools. Okay, so they were determining the shape of the moon. It's not a perfect sphere, nor is Earth. Okay, but how is the density of mass distributed? Okay, and we learned from that the far side of the moon, the crust is 30 kilometers thicker on average. That's weird. But it also links up with the far side is very different, right? And there's also a connection between the changes in gravity to the much larger impact basins. And I'll say that even though the large impact basins on the near side, they're filled with lava, right? Cooled lava, new rocks. But this giant basin on the far side is not. Why? We have a lot of theories, but we're not confident in any particular one. We can talk about that in the Q&A. I won't hit them too hard. This is a very awkward view. The South Pole is here, and this is the far side. So this is just a zoom-in view of South Pole Aitken Basin with a topographic map. But impact craters are incredibly important for studying all of the solid surfaces in our solar system, not just the moon. But we actually use them as a tool to date the surfaces of solid bodies. So the concept is the distribution of the size distribution of those craters and then the density of them. So if you have a region that has more craters, it is going to be older than a region that has less craters. Pretty straightforward, right? Then we have a tool that actually measures and then does the calculations. But essentially, it's more craters older. Okay, so you can tell, if you go back to this, which side of the moon is older? Far side, right? Because it's mostly that ancient lunar crust. And then because we have ages for some of the rocks and some of the craters on the near side of the moon, because we collected those samples and we brought them back, we don't have to just say, this one's older, this one's younger. We can now calibrate that, and we have a really good idea of if it's this many craters, it's probably about 4 billion years old. If it's this many craters, it's probably closer to 3. And the age ranges that we got back from the moon are between 3.5 to 4.5 billion. Most recently, China landed in the Oceanus Procellarum here, somewhere around there. It did like a grab and go, brought a little bit of sample back, and we always thought that this was going to be the youngest deposit on the moon, and it turns out they were right, assuming their age is right, because it's only like one data point, right? We need more to be confident in it, but it came back about 2 billion. So the last time the moon had any kind of volcanic activity that we know of, because we have a very small sampling size, right? We only sampled a couple little spots, so about 2 billion. But for the most part, the moon was inactive after about 3.8 billion years ago. And that's why it preserves our history and its own. All right, I said I would come back to water ice. So Lunar Prospector had an instrument on board called a neutron detector. It basically measures for hydrogen, which is part of water, right? H2O. And it originally detected water ice, and then we used that moon mineralogy mapper that we looked at before, and it also detected what we call hydroxyl, so basically a version of a water molecule, in the lunar poles. So most of the moon is pretty dry, but around the poles, you're getting water molecules on the surface. But understand that this is only measuring like the very surface, okay? Not the subsurface, not what's in the rocks really, but what's just sitting on the rocks. And it turns out with some other data, so now there's multiple spacecraft looking at this, there's actual water cycle on the moon. And this is really cool. I only just learned this not that long ago. This is not my area. But there's a water cycle that is connected to micrometeorite impacts on the surface of the moon. Every time we have a meteor shower, it means that the Earth and moon are basically in their natural orbit passing through the trajectory of a comet. So all of our meteor showers, like the Perseids and so on, that's because there's a comet that comes around and then it leaves a bunch of dust. When the Earth and moon kind of go through that during the year, it's always the same time of year, we get a meteor shower. But the moon has no atmosphere. So there's no meteor shower. You'll never see a meteor on the moon. There's no atmosphere for it to burn up in. It hits the ground. Even something fist-sized will hit the ground. Fist-sized thing on Earth never hits the ground, burns up. So now all these little micrometeorites, when they hit the dirt, they're essentially releasing gases, what we call volatiles, and those gases are then basically measured with our instruments. And so we linked every meteor shower to when we observe more water on the moon. So we know that those volatiles are being released from these impacts. Now, any water is going to immediately sublimate if it's in sunlight, and the same thing with hydrogen, that is just sticking, like molecules just kind of sticking to the surface. Solar wind usually blows them off or it gets sublimated, okay? But near the lunar poles, we have what's called cold traps, and they're in these permanently shadowed regions at the poles. And this is the big draw back to the moon. This is the big draw to the south polar region, is because we believe, and we've measured in various other ways, that a lot of water has been basically accumulating for billions of years in these permanently shadowed regions. The reason is the moon is only tilted about 1.5 degrees, its axis. And so the sun at the poles is always really low on the horizon. And so there's some areas that are always illuminated, but at very low lights, and some areas that are permanently in shadow and have been since the early days of these craters were formed. And so all of these blue spots, this is identifying all of the permanently shadowed regions in the South Pole. This is where hydrogen was detected, and they're connected to those same shadowed regions. And this is the actual crater names. The South Pole is right in this Shoemaker crater here. Okay, so all of this water that not only accumulated through this water cycle, but also when the moon was volcanically active, and when it once was actually much closer to Earth, there's actually an early atmosphere on the moon, and it was exchanging with atmosphere on Earth. And so way back in that time, when there were more volatiles on the moon, we believe that they got stored in here, because it's possible that there's actually a significant amount of ice here. It's probably not very pure. It's probably mixed in with some regolith, so it's going to be a bit of a challenge to get it out. But if we can get it out, it'll be huge. Why? Because it is a resource we can use for so many different things. Okay, so you've got water. Water to drink for your astronauts. You break it into oxygen and hydrogen. Liquid hydrogen and liquid oxygen is the best rocket fuel that we've got. Okay, it's the most efficient rocket fuel. If you can refuel in orbit around the moon, that is a game changer, and that's really why we're going back to the moon. Okay, but you also have oxygen for breathing. You can then recombine oxygen and hydrogen in a fuel cell, so now you have a possible power generation. Okay, so water is huge as a resource that we can use in place. And it's a lot easier. Let's say, like landing on the moon to refuel is not feasible, but if you could refuel in orbit, that's huge. Because launching something off the moon, which is about the 1/6 the gravity of Earth and no atmosphere, no friction from an atmosphere, is a lot cheaper than launching something from Earth. When you're launching a rocket from the surface of the Earth, 90% of the mass is fuel. And by the time it's in space, most of that's gone. So getting a lot of fuel in space to then forward onto Mars is really tricky. And the biggest part is, once you get to Mars, like we can get to Mars, no problem. You need enough fuel to be able to launch off Mars and come back, right? Because we kind of want the people back. And so that's the biggest challenge, is we can get to Mars because we can get enough fuel in an economic, practical way. If first we have to get to the moon and confirm there's as much water as we think there is, then we got to figure out how to excavate it and convert it into the fuel that we want. So you have to have infrastructure in place to do that. I know, very ambitious plan, not denying it. And then you got to get it into orbit. So there's some, again, incremental steps. So it'll probably be a while before this all comes to fruition. But that's not the only thing that we can use in place. But this is the idea of a sustainable lunar exploration, is because we can use things in place. We can also get all sorts of different things out of the minerals on the moon. Oxygen, you can pull oxygen out of the rocks. Most rocks on the moon are oxides, so about 50% oxygen. But again, processing would be a challenge. But there's iron, magnesium, titanium. You can actually take lunar soil and use it in a form of concrete. You just have to have a way of heating it. You could 3D print a whole habitat using regolith if you process it right. Okay, we got some really cool ideas coming out of this. I also mentioned that There are other volatiles that are probably in those traps, but we're not entirely sure what they all are. But if we go by what we know about the moon, this is the general list. The other thing that we are fairly confident we could do something with, and actually Harrison Schmitt, very advocate, that Apollo 17 geologist, advocates for this, is helium-3, which is another potential power source. We can use this funky isotope of helium to basically do nuclear fission, another power source. All right, so that's why we want to go back to the moon. We want to get the water ice. We want to use the resources that are there, and we want to do it at the lunar poles because that's where we have to actually get the water. And these are the current 13, but they've just dwindled it down to 9, like 2 days ago, so I didn't get to update my slide, landing site suggestions for our return. You'll see that all of them border on partly fully illuminated spots and like a cold trap. And so there's always that. It's not just that, though. There are a lot of geological reasons in which we want to go to the South Pole, but also to sample that big basin, South Pole Aitken Basin, and also the cratering across the moon. We know that there's a lot more cratering that happened about 3.8 to 4 billion years ago. This is a period that we call the late heavy bombardment. But there's some conflicting evidence that this is a thing or not. But it also coincides with the origins of life on Earth. And so understanding that big picture and connecting it to the origins of life, having more samples from the moon can add to that story. It's just another piece of the puzzle, or another hopefully couple pieces to the puzzle. So to get into what that return entails. So the Artemis Accords, so there's already a treaty, an international treaty on the peaceful exploration of space, essentially. But the Artemis Accords are a new collaborative agreement, we're going to call it, for peaceful purposes, but also for transparency, interoperability. So like I said, if you got a Chinese or, I don't know, a Colombian lander, that's probably not going to happen, but let's say any of these countries that sign on that's in trouble or needs a hand or want some advice, they will exchange information and they'll be very transparent. They're going to share their science discoveries with each other, maybe not right like as soon as they discover it, but there will be protocols in which to do that. This is not updated. There are actually 47 countries that have signed the accords. Chile was added 2 days ago. And the plan overall, and like I said, they've already started sending robotic missions to do more work in trying to find that water ice. But it's going to involve a space station around the moon called the Lunar Gateway. It's basically a mini international space station in which Canada is contributing yet another robotic arm, because that's one of our specialties. So Canadarm will be added. And so mini space station that's going to orbit in a really funky, very elliptical polar orbit, okay, over the poles, so that when they're going down, when they are going to go down to the surface, they're already going to basically pass by the pole and then land that way. And the Artemis program has begun. The actual first, actually I'll jump to that in a second. Canadarm3 will basically be a smaller but souped up, more advanced version of Canadarm2, which is still operational on the ISS and has been for decades. It'll also have like a toolkit, kind of like Dexter, our more dexterous robotic arm. But the big difference is because it's operating really far from Earth, it'll be around the moon, it can't be teleoperated constantly. There's not always going to be astronauts on this space station, probably only about a month a year. So it has to be, for the most part, autonomous. And that means AI and machine learning is going to be built in, and they're developing that right now. So the hardware is the easy part, the programming of it is the challenge. It has to be able to maintain this space station without human interference. Another, like I said, ambitious plans, ambitious plans. All right, Artemis 1, they designed a nice new rocket called the Space Launch System. It's this, ugly orange thing here. It's kind of the equivalent of Saturn V, although they're saying it's much bigger and better, but it's about the same size, just a little bit more power. But they successfully sent this up, and the Orion spacecraft for 26 days went around the moon a couple of times and came back, plopped in the Pacific Ocean. And if we had astronauts on board, they would have got back in one piece. So Checkbox, Artemis 1 done. So that's kind of the equivalent of Apollo 8. Next up, Artemis 2, same thing. We're going to do same vehicle, launch, go around the moon, but there's going to be 4 astronauts on board, and this is happening September 2025, next year. Okay? Not only that, there's going to be a Canadian on board. So for our contribution for that Canadarm3, we earned 2 seats to get to the moon, 1 around the moon, and the second seat is undetermined at this point. But the first seat goes to Jeremy Hansen, Canadian astronaut Jeremy Hansen, who has not been to space yet, but he was selected in 2009, so he's been very, very patient. Along with 3 other astronauts, you'll notice 1 is a woman and 1 is a person of color, and they also intend to keep those diverse crews when they start landing on the moon as well. Jeremy's backup is actually another Canadian astronaut, Jenny Gibbons. We have 4 current active Canadian astronauts. All right, so he's launching next year. Pretty cool. And then Artemis 3, already right after that, is the first mission they're going to put boots back on the moon. All right, so the landing, I want to call it landing spacecraft, ascent and landing vehicle is a SpaceX Starship at the moment, but there are other contracts in play to have other ones. But this is the likely case scenario. It's going to be putting boots on the ground on the South Pole in September 2026, assuming Artemis 2 goes well. So if they learn lessons and they have to change something, they'll delay that. And Artemis 2 was already delayed because they learned some lessons from Artemis 1. Even though everything went well, there were still a couple of little things they were like, we better check that. All right. And now we talked about the approach to lunar exploration. So I'm going to go on this side for this, because don't worry about seeing, I know they're like little tiny things in this diagram, but the essential is 3 phases. First phase, boots on the ground. Second phase is explore and become more mobile, become more adapted to operating and exploring on the surface. That includes more robotic missions. That includes rovers, both pressurized and not. That includes installing, your first habitats or laboratories on the surface. If they're going to start off with 2 astronauts, there'll be a crew of 4. 2 astronauts stay in the capsule in the orbit. 2 astronauts go down in the landing vehicle. So there'll be just 2 people that land the first time. Then they go up, re-meet their compadres, and head home. And that'll be the case, 2 to 4 astronauts for the first couple of years into this. But there's going to be Artemis 4, 5, 6, unless somebody cuts the funding, which, because it's international, and because now another huge different piece of the pie is commercial entities are now part of the picture. Some of those missions to the moon are commercial missions to the moon. And actually, NASA has a commercial lunar payload services where they'll launch a payload, somebody's got a lander, and you can pay to have your instrument put on, or your rover. And Canada actually is contributing a couple of those things. We've got cameras on one that's going to be launched this year. Okay? There's a lot more going on. There's a lot more engineers and scientists involved in little bits and pieces throughout, but I can't go over it all. And then eventually, once we've got sort of living on the moon established, at the same time, getting an in situ resource use pilot plant, power station, so all of the essentials that they really need. And then they're going to get into how do we stay here longer, more infrastructure, more manufacturing of things. The other thing Canada's doing as part of that is contributing our very first, all our own rover, designed and built by Canadensis, and NGC Aerospace is also contributing some software, but that's him. That's our Canadian little rover. And we actually have the science team is dominantly Canadian scientists, and the lead is actually my PhD supervisor. And it's going to be able to drive into those permanently shadowed regions for about an hour. It'll be able to survive 2 lunar nights. 1 lunar day is it's 14 days, Earth days of night, 14 Earth days of dark. There is no dark side of the moon. Okay, it's the far side. It's no such thing, because the whole moon does get illuminated. Think moon phases. So, our scientists, they get irked every time they try and put that in a movie or something. It's also going to be able to measure hydrogen, so it's going to be looking for water ice. It'll learn a bit about the geology and then the temperature within those permanently shadowed regions, which can get down to like minus 220 degrees Celsius. That's kind of part of the coldest regions in the entire solar system are in these craters, okay? We're also contributing a lunar utility vehicle. Our rover is going to launch no earlier than 2026, but probably get pushed. And this one probably 2028 or longer, but it's going to depend on sort of the whole program, what makes sense. During the intro, someone mentioned that I participate in analog studies. So I was paid by the space agency in my previous life to basically run simulations on, rover operations, simulated astronauts, and then actual science, remote sensing, testing out suits, testing out instrumentation. How portable is this? What instrumentation is most effective? If we want to answer this question, what type of spectrometer is the best to use? Things like that. And having teams of engineers and scientists work together because they don't always talk the same language. And that experience is invaluable because there is no space exploration unless you get those two parties working together. We also train actual astronauts. So this is a couple of my expeditions. Most of my work is in the Canadian Arctic because there's impact craters and because it's a very lunar-like environment or Mars environment. It's an Arctic desert. It's cold. There's no vegetation. You're really far away from help. It's expedition training for geologists and astronauts because you're put in a small team. You're put in a very high-risk environment, very far from help, but you're also expected to deliver this high degree of quality of science, right? So very similar in that way. They actually get the astronauts to do all sorts of things. They'll go to underwater habitats. They'll go spelunking in caves. So this is just one of many. But in this case, they also learn about impact crater geology. So this is Jeremy Hansen, who's going to be going around the moon next year. And Oz, my supervisor that I mentioned. We're in this crater here. So we're camped. This is us. This is me in blue. Look at another outcrop. This is astronaut Joshua Kutrick, another Canadian astronaut. He's going to go up on the ISS next year. And this is Matthew Dominic, and he was actually just on Crew 8 that got back from the ISS and plopped into the Pacific last week, or actually just a couple days ago. Thankfully, they came back all right. This is just an example of meteor crater, another one of their training sites. Another thing that Canadians do is, and where's back there, is space medicine. We put a lot of funding into developing space medicine and remote healthcare. This is the type of thing, it's not just, how to do remote healthcare, but it's developing technologies, just like this one that David Saint-Jacques is wearing, like biomonitoring system. He just puts on his tank top, but then we actually, it's all built into the fabric. We can monitor his vitals. So things like that, these are Canadian made and tested already in space developments. Everything from diseases, information that we can, like osteoporosis, because you actually lose a lot of bone when you're in space. The list is never ending when it comes to space health and medicine, but there's a lot of Canadian scientists on that, and deep space food technologies. So if we're gonna go to the moon or Mars, we're gonna stay long term, we can't ship all of the food. It's just too heavy, it's too pricey. So we have to find technologies, find ways to do that, and those same technologies can be used for our remote and northern communities in Canada, and so we're giving back. Okay, it's not like that money is just going to space. Almost all of these technologies are reused in some way to benefit the people of Earth. You guys use space technology every single day. Every time you take a selfie with your camera on your phone, every time you check your Fitbit, that is all space technology that has been reused on the surface of Earth. All right, now I'm gonna jump to Mars. I might speed through this. I know we started a little late, but it's not like we're gonna go do this all on the moon and then start from scratch to do the same thing to Mars. Because we've been studying Mars and sending spacecraft to Mars for 58 years. This is the family of spacecraft that have been sent. Orbiters, landers, rovers, and there's currently 2 rovers still operating on the surface of Mars, 7 orbiters, and there's 1 lander, a Chinese lander that I think is still beeping. So Perseverance and Curiosity are still roving on the moon. Roving on Mars. And we know a lot about Mars because, like the moon, we've been studying it for quite a while. It's a little bit smaller than Earth. It's now kind of cold and dry. It does have a very thin atmosphere. It's about 1% of our atmosphere. So very, very thin. It's dominantly carbon dioxide. It has a really broad range of geology. There's canyons, there's ancient river channels, there's volcanoes. The largest volcano in the solar system is there, 26 kilometers high. It's called Olympus Mons. And you remember I said there was 14 kilometers difference on the moon? Huge difference between the top and the bottom. Like, this is the Marianas, this giant trench here, not the Marianas, that's Hunter's. This is the Tharsis region. It is really, really deep, but then you have the highest volcano very, very close. There are 4 very giant volcanoes on Mars. What we do know of Mars is that in its history, probably about 3.5 billion years ago, it was very much like Earth. It was this blue marble. So was Venus. Maybe John talked about this, but once upon a time, Venus, Earth, and Mars were all blue marbles. They had liquid water on their surface. And all 3 bodies evolved very, very differently. Why? Why is Venus now the hottest planet in our solar system? It has a runaway greenhouse effect. It has a toxic, crazy, thick atmosphere of CO2. And Mars went way the other way, and we're somewhere in the middle. Okay, Mars is cold. It lost its magnetic field. And we think it's because it no longer has a magnetic field because it cooled down because it's smaller. When you lose your magnetic field, then your atmosphere is kind of open to being blown off by solar wind. So year after year, it lost gases from its atmosphere, and that's why the atmosphere is so thin. But once upon a time, when it had a thicker atmosphere, liquid water would have been stable on the surface. Okay? And that's the time when we think Mars was habitable. Now, there's still a lot of water ice on Mars, way more than the moon, a lot easier to get to. There are polar ice caps. Some of it is CO2 ice, okay? But a lot of it is water ice. Both caps, the northern cap is there all year long. Southern cap disappears entirely during the summer. And Mars does have seasons. It's inclined about 25 degrees. We're 23, 25. So it does have really cool seasons. It has winds. I don't know if John, which sense he did for Mars, but we've actually taken a microphone and we can hear the winds on Mars. Really cool. But there actually is subsurface water ice, pretty much not in the mid-latitudes, but about down to here in both ends. So we got some options. We even have a Canadian instrument. There's lots of Canadian instruments that were involved in looking at Mars, but we were the first instrument that detected snow falling on Mars too. Very cool. Another topographic map of Mars. You can see this is that giant Olympus Mons volcano, canyons. This is Hellas Basin, the largest impact crater. You'll also see there's also what we call a dichotomy, like the moon, 2 very different terrains. This one's nice and smooth and low, and the rest is very different. But some of the ways in which we detected and confirmed that there definitely was liquid water on the surface of the moon, like this has been proved dozens of times. By even just the MER rovers. This is Opportunity here. This is just some of the things. There are sedimentary rocks on the moon. Shales, sandstones. You can see the layering in the sedimentary rocks. There are what we call hydrated minerals that are minerals that can only form in the presence of water, and there is water in their structure. This is calcium sulfate, and that can only form as a precipitation as evaporation of water occurs. We've actually seen these minerals be precipitated because we have before and after shots. So it's still happening today. There is some surface water that kind of comes up, sublimates immediately, but it's still leaving back behind traces. Curiosity, the other thing we know about the moon, and you can see more sedimentary layering back here, has drilled into the moon some 47 times, I think now. The moon is red, Mars is red, but it's actually just because there's this iron oxidized dust that covers most of the planet. As soon as you get through that couple of millimeters, the Mars is many colors. I'm mixing up my moon and Mars. I'm all Mars right now. It's okay if I switch. But you'll see that there's grays and beiges and browns and etc. So you actually have a variety of volcanic rocks on Mars and a variety of sedimentary rocks so far. We have not yet found metamorphic rocks. Those are ones that are deformed through heating and pressure, but it's probably because we're gonna have to drill a little bit lower. And the Perseverance rover that launched in 2021 and this is its current path, so this is where it is now. It landed in what's called the Jezero crater. This is an ancient impact crater, about 45 kilometers long, but at one point it was filled by a lake. A lot of our craters on Earth are filled by water too. That water is now gone, but the sediments are there. You have a river channel coming out, dumping out in this delta material. This is a huge delta, it's all sediments. And so the reason they sent Perseverance, we had proved that Mars was once habitable. We proved that we had water, liquid water was on the surface, and there's water ice now. We've got all of the key elements, energy sources, heat, everything we need to say life could have survived there. What we don't have is evidence of fossilized life, and that's why Perseverance was sent. So it's looking in the delta because those sediments are deposited really quickly. So let's say there were algal life. It would have been preserved. The best case scenario would be in a delta because it's rapid sedimentation. But we'll only ever be able to confirm confidently when those samples are returned. And so that's what Percy's doing. He's going to drop some samples, and there's going to be a Mars sample return hopefully soon because they keep revamping how they're going to go about it. But something is going to go back and get those capsules and bring them back. This is Percy here. Also with Percy, we sent a little tiny helicopter on Mars as a test to see if we could fly on Mars. And the answer is yes. Okay, I'll come back to that. I'll come back to Ingenuity. His name's Ingenuity, but this is Percy checking him out. Also on Perseverance was an experiment called MOXIE, and this basically sucked in the CO2 from the atmosphere and converted it to oxygen that is breathable. It was to test to see if we could actually convert it, and it worked perfectly. We have made oxygen on the surface of Mars, so we know we can. Only about 5 grams, but because it was like a very small version of what we would need if we were to put an astronaut on the surface, but all we had to do was demonstrate we could. So that's a box checked. And I have, I think, 2 more slides. Yeah, this is just if we'd like to see. Is it gonna do it? Is it playing? We'll skip ahead. There, so this is Ingenuity here. This is its very, very first flight. It was only supposed to fly 5 times to see if we could do it. It's an ultra, ultra light helicopter. It's only about this big, really tiny. It, there you go, lifted up, went down. After those 5 flights, it was so good at flying on Mars, they changed the mission and turned it into a reconnaissance helicopter. And then it basically scouted out all of the trucks. And in the end, it did 72 flights before, cracking a blade. So very cool. We have done power flight on Mars. Pretty impressive. All right. And so, this is the end goal, the permanent habitation on Mars. So you can see how everything that we do on the moon is practice, is a testing ground for Mars. And the biggest difference between the two, because we've already studied the environments, we know that we can do it to the moon, is distance. Getting to the moon only takes a couple of days. Something goes wrong, doesn't take that long to send another cargo ship to give them more food or whatever. But getting to Mars takes 7 months. And that's the fastest trip, is just under 7 months. And there's only a 2.5-week launch window in which we can actually send a spacecraft to Moon every 26 months. So you can only actually launch something to Mars about every 2 years. Because otherwise, Earth is going to be on the other side of the sun, and then it'll take you a lot longer, and it'll be way too much fuel to try and get there. So you have to kind of use the orbits to your advantage, and that's 2-week window every 26 months. All right, so with that, I'll say thanks.
Okay, I don't know where to begin. Cass, you're a walking marvel of knowledge and understanding and enthusiasm and Canadian pride. Yay. So I want to thank you for all of
Thanks,
that.
Thanks, guys.
I'm sure there have to be some questions out there. Okay, so we'll be running around and bringing you the microphone.
Hi. My first question is about September. You mentioned two things were happening in September. Why is that? Is the moon the closest then?
Oh, no,
that
you
time
can go
of
to the
year?
moon anytime.
Oh,
Thankfully, yeah, there is, I mean, the moon does kind of go further and closer away, but you can go anytime. You just change the orbit a little bit depending on the time. But they can, it only changes the what we call the apogee, or in the perigee. When the perigee is when the moon is closest to Earth in its orbit. That kind of comes and goes fairly often, like once a month. So
okay.
it's
So
no
the
problem.
September has no significance.
They do. There is an ideal launch window, but it's not just about how close is the moon. It's because we want to land. So you remember moon phases, right? So it's when is it going to be lunar daytime? Because you want to land when you can see. So usually it has to do with the timing of orientation with the sun, and not so much the distance between the Earth and moon.
Okay, in September you,
want-
have harvest moon, which is a big moon.
Exactly. Yep. Yeah, and that's typically when you have that larger full moon. That is when the moon is closer in its orbit.
Am I correct in saying that the moon doesn't spin on its axis?
It does spin. Yep. It just spins at the same, at like basically 1 month. So it spins on its axis. It does have a day-night, but because it's the same, it spins at about 27 days, which is about the same time it takes to go around Earth. So we never actually see it spin because the same face is always facing us. But it is spinning, except for we're spinning with it.
And is there an obvious reason for that? Like it's the same as...
It's because it's tidally locked, essentially. Yep. Yep.
Hi. If Apollo 11's lander ran out of fuel, how did it get back up to the mothership?
So the basically the retro rockets that brought it down, that's a different fuel than the actual ascent vehicle. So that never ran out of fuel for the ascent vehicle. Different cylinder, if that makes sense. Yeah, that they always saved. They would never have botched the landing if they thought they couldn't take back off. Knock on wood. Yep, but good question. Mm-hmm. Hi.
Hi, I'm wondering how you first became interested in this.
So I started off. I started an undergrad in physics, and then I decided that was not a whole lot of fun. Too much sitting at a desk doesn't work for me. I prefer to be outside. So then I switched into geology. I loved the outdoors, and so if you can spend your summer studying rocks outside, and then you spend your winter in the lab, it's kind of like best of both worlds. You don't get bored. But then when I started a master's degree, the project that was offered to me was in an impact crater. So I was studying rocks, but then it had this link to space. And coming from a small town, I never thought space exploration, and someone else is from my small town here, never thought scientists or space exploration was in the realm of possibilities for a career. But until I got on the space train when I realized I can do rocks and space. And then I was just hooked. Every opportunity that came up, I did. And then I continued on that impact crater phase through my PhD. And then I got a job managing these simulated missions and got a lot of experience. And then I just kept getting pulled for things. I got really lucky opportunity-wise. It's about timing. So, but yeah, I got on the space rock train and never got off.
I was wondering, considering Elon Musk, is he a signatory to this collaboration?
Is he signatory? Yes. In the sense that he is his company, not him. Really, he's not doing all the work. But his company, SpaceX, and other companies, they are being contracted to do some of this work. And then he himself, not as part of Artemis. I mean, he's developing, Starship, that is meant to be our ascent vehicle to get down to the moon. That's really what's giving them the funding to develop Starship. But his personal goal is to then use that same craft and land on Mars. And that is not directly connected to the national space agencies. That's just his personal goal. But through being contracted and paid by entities like NASA, he's able to have the funding to make it happen. So he's a part of the picture, but he's only running his own show in his own way in a bubble. That is. But I will say, you know, he's a very polarizing figure. He's not my favorite person, but I will say that he did do huge things for the advancement of rocketry. Not as not the person that's sitting down doing those calculations, but as a driving force. And it is really his company, how they started out reusing rockets that has started making space exploration more affordable. And so I'm always going to be thankful for him for that, but now he's kind of gone off on a tangent.
A few years ago, it was announced that they discovered life on Mars. That went away. What happened there?
Okay, so there's actually a few times, but are you talking about the meteorite? Maybe. There are a few controversial bits of evidence. The one major one was they found this tubular feature in a Martian meteorite. So a meteorite, a rock that was on the surface of the Earth, but chemically we know that it came from Mars. That we detected the morphology of something that looked like it was probably a fossilized life form. It's still debated today. There are still two camps that aggressively debate this. And so we don't know, but it's definitely not alive now. That's what I can tell you for sure. And that's not the first time. What we have detected confidently is water ice, and we've also detected organic molecules many times over. And one of the cool things just recently that the Perseverance rover, which is part of his job, or her, whatever you like, identified organic molecules and those hydrated minerals in the same rock. So in the same space, they've got more ingredients that could support that there was life there. But we have not yet, confirmed without a doubt. And like I said, for us to do that, we really need a sample back. We need to know that the huge thing that differentiates having a Martian meteorite and having a sample that we collected and brought back is we have no context of where that came from, how it formed. We could get an age for this rock, but I don't know what that means. What is that? What does that age represent? Is it an impact? Is it, where did that come from? So we need context, and that's why collecting the sample, doing all of the work on like what outcrop it comes from, what is all around it, and then using that sample. As a geologist, with the exception of space exploration, there's a hard and fast rule. You never collect a sample unless it's you that breaks it off of the outcrop. If there's just like gravel on the ground, you pick up a rock, that means nothing because you don't know how far it traveled, how long has it been there? You can't answer all the questions.
Oh, thank you. Yes, do you know?
I can hear you.
Do you know the frequency of meteorites hitting the moon? Is there any idea?
Every day, all the time.
Yeah. The reason I'm asking is if you're putting some buildings up there, the chance of it
Okay.
whacked.
This is a wonderful question, and I didn't actually get into that. I didn't actually get into radiation shielding, and I didn't get into protection against micrometeorites. So excellent question. Yes, so small stuff, like we said, the water cycle is caused by this. Small stuff hits the surface of the moon all the time. No magnetic field, no atmosphere to protect it. But same thing for any spacecraft that kind of goes beyond orbit. There's always going to be small stuff that is impacting. The trick is, if you have even a tiny little thing, but it's moving at like 20 kilometers a second, it can do some damage. I will tell you that even the solar panels on the International Space Station, they're full of holes. But one little hole might not cause the whole thing to fail, right? So the idea is whatever we build it to be able to resist a sort of a bare minimum of those type of impacts. And so there'll always be a protective shield that will, and we actually are developing materials that can absorb these smaller impacts. If there's a big impact, there's not a whole lot we can do. And those do still happen, but on a much less frequent time scale. We also have to protect against solar radiation. Our magnetic field protects us from a lot of radiation, but on the moon, the spacecraft, the electronics, and our astronauts are going to be exposed to ionizing radiation, especially on the trip to moon and back, or to Mars and back, which is a lot longer. Our astronauts are going to be in space, unprotected, outside. The International Space Station, it orbits within our magnetic field. So they're actually pretty well protected. The only time they're in danger is if there's like a solar flare or a coronal mass ejection, these explosions on the surface of the sun, which we're getting a lot lately. I don't know if you've noticed the uptick in aurora, but that's why, because the sun is in its active, it's on an 11-year cycle. And so we're actually approaching the maximum. So the sun's really active. It's bing, bang, boom. It's just showering us with charged particles, which are lighting up the sky. But those same particles affect communication. They affect high-frequency radio. Not only can they mash up other things. And so on the surface of the moon, if you have a solar flare, because you've got no magnetic field, now you're astronauts, you need some special shielding. The bonus is, we usually, if there's a flare that's going at the speed of light, not a whole lot we can do. But if there's a coronal mass ejection, which is just a different kind of eruption, but actually sends mass towards us, that, because it moves a lot slower, we usually have 2 or 3 days to prepare for it. And so you just send everybody inside. Some of the ideas are we build habitats in lava tubes. Not a whole lot of lava tubes in the south pole of the moon, but there are in other places on the moon. Or we bury our habitats under regolith, a certain amount of thickness that will protect both from radiation and micrometeorites.
You've answered my question.
Perfect. Awesome.
At the start of your presentation, you mentioned the economical benefits of lunar exploration. Causes me to wonder if there's any kind of economic return projected from these efforts.
Not my area, but I'll try. Right now, the space industry is booming. Every space company in Canada is growing because they're being contracted by national agencies that are given the funding to do this. So so MDA, that's building Canadarm, for example, now just got a whack load of cash to build this instrumentation. They're hiring engineers left and right. And that's sort of within Canada, but across the board, it's booming. And that's partially because companies, like I said, can get there cheaper. Right now, they predict the space economy will be on the order of $30 trillion. Yeah, shocking. You want the return. Where's my return on investment? It's a good question. I don't know the numbers exactly for the return on investment. I think it'll be a delayed return, absolutely. And some of that return on investment is just reutilizing those same technologies on the surface of Earth. So like I said, most of the stuff that's being done can be reused on Earth and sold off in that way as well. So it's kind of there's a cycle of what we can do.
I'm interested in the sustainability idea of the water ice as a fuel resource.
Mm-hmm.
I'm curious if there's any idea, it being ultimately a finite resource, is there enough for 10 years of fuel, 1,000 years of fuel, or do we just not know that?
We got to figure it out. Right now, the estimates are that in those permanently shadowed regions, there's somewhere on the order of 5 to 10% water ice. Like if you were going to collect a rock or collect a sample, it would be about 5 to 10% water ice. That's not a lot, but it is if you're thinking on the order of like gold. Okay, that's a lot. So it totally depends. But the one thing is it's not that, with the exception of turning it into rocket fuel, the actual resource, we can recycle a lot of it. So for example, on the International Space Station right now, 75, actually, no, it's more than that. Yep. Most of the water on the International Space Station is recycled. We actually take, the bathroom. Today's urine becomes tomorrow's coffee. If you've ever heard that expression, there's actually 75% of urine that is recycled back into the drinking water, and the other 10% is actually filtered out of the air. It is from perspiration and from our breath. We actually recoup that water as well and turn it back into drinking water for the astronauts. This is just one example of the ways in which we can reuse water, oxygen, and or hydrogen. There are fuel cells in operation, electrolysis tools also functioning on the ISS. So these are some of these technologies we have been playing with for some time. We just got to get better at it, and we have to be more efficient. But an excellent question. I will say that most of the things they are developing, a lot of it is like, how can we do it? What is the most sustainable way to do it? The other thing is technologies, even though we've advanced our technology significantly, you don't want to add too much complexity at the same time, because it has to be something that doesn't break often. You ever, like download a new software and then it's just so buggy because it's new and it hasn't been, do you know what I mean? That's not the type of thing that we want to send. We want to send something that is robust, that with the fewest amount of moving parts possible, so that it's unlikely to break.
Okay, Wayne, we're going to let you have the last question of the evening.
What is the timeline for the various Mars projects?
If you ask Elon, it's really soon, but his Starship, is still in its orbital testing phase, and so he was hoping like now, but it'll probably be another decade away for him to test out that theory. That's my guess. But there's no specific timeline. Well, there is and there isn't. It's very nebulous for we're definitely going to get to Mars now, because we have too many questions that we need to answer on the moon first to guarantee that we're getting there. Everyone is optimistic, but we generally tend to be in space exploration world, assuming we're right about the water ice, assuming we're right about being able to have enough to get us there. So the timeline is this. And if you ask, let's say you asked a NASA administrator or Canadian Space Agency. Yes, we have a space agency. I didn't mention that, but for those who don't know, we do. It's just smaller and we have less funding. They'll give you a different answer every year. So it was the 30s, like the 2030s originally. But if I'm answering honestly, it'll probably be more like 2050s. So I don't know. Well, I'm hoping that we get there in my lifetime.
Okay.
Never know.
Thank you, Dr. Cass Marion.
My pleasure. Thanks, guys.
Whether or not we make it to Mars in your lifetime, you certainly are going to meet your goal of educating the Canadian public about space and science, and do it in such an enthusiastic and optimistic way. So thank you so much. Next week on Thursday evening, the NLC welcomes Marc Garneau, and he'll be at the Capitol Theatre in Port Hope starting at 7:30. His talk is titled, "Why is Space Important?" And tickets have been selling very well, but as you know, the Capitol Theatre is a very large venue, so please encourage your friends. There are still a few tickets left. Also, Mark will be signing his new book called A Most Extraordinary Ride, and you can buy advance copies, I understand, at Furby's Books. Now, finally, I would like to thank the 20 people that added their support to our 2024 Connector campaign since we last met last week on Thursday. Our goal this year is to surpass the 125 people who helped provide predictable funding for the NLC program this year. Thank you so many in this room. Thanks to you, we're about 3/4 of our way to meeting our goal. In closing, if you love learning from leading experts like Dr. Cass Marion about relevant 21st century topics through an interdisciplinary lens, then please consider stopping by our Connector table back at the corner on your way out, or by visiting our NLC website when you get home. We can't do this without you. Thank you all so much. Good night.